All right, if you thought chemical bonding 1 was fun, perfect, because we've also got chemical bonding 2. And it's different and a little bit more conceptual. The first initial bits of stuff, I think, is not too crazy, not too difficult. We will get into some bond theory stuff. That starts to be a little bit weirder. The molecular orbital theory, I think, is arguably the hardest part of the chapter. Okay, so valence shell electron pair repulsion theory. If you've taken chemistry before, you have hopefully learned about valence shell electron pair, or VSEPR theory. Some people call it VSEPR theory, and I think they're wrong to do that. So that's my personal take. So valence shell electron pair repulsion theory. The valence shell is our outermost atoms. So in any given atom, outermost electrons, outer shell, our highest principal quantum number, our highest n number, our highest row number. That's our valence shell. Electron pairs, any group of electrons. What charge do electrons have? They're negatively charged, and so it makes sense that they would repulse or repel each other. So all that valence shell electron pair repulsion theory is saying is that our outermost electrons will form electron pairs in the form of single, double, triple bonds, as well as single electrons and lone pairs. And because those are negatively charged, they will repel each other. That's all that we're saying with valence shell electron pair repulsion theory. Now, it's a little bit more complicated than that when we get into the details, but that's the basic idea. All electron groups repel each other. So valence shell electron pair repulsion theory, VSEPR theory, is like, what does that do for us? What does that tell us about the shape of our molecules and all that sort of good stuff? An electron group is any group of any size of electrons. It can be a lone pair, 2 electrons that are localized in an atom. It can be single bonds, it can be double bonds, it can be triple bonds, it can be a single electron like in a radical or an odd electron species. All of those count as one electron group. Triple bonds count as one electron group. A single electron counts as one electron group. They all count the same. They don't all behave the same, but we count them the same in terms of electron groups. Repulsion groups between electron groups on interior atoms, like our central atom, we are usually going to talk about it as a central atom, determines geometry, determines the shape. There are 2 types of geometries that we'll talk about. There's electron geometry, what the electron groups are shaped like. There's also molecular geometry, what does the molecule itself look like, since electrons don't really take up space. And that's the one that's arguably more important. The preferred geometry, the preferred shape, has maximum separation of the electron groups. The electron groups, since they're negatively charged, repel each other. They want to get as far away from each other as they can. So they do, because that's where they'll be the most stable. If you've ever tried to put 2 magnets together with the opposite ends, the negative sides or the positive sides, and they're repelling each other, it's really hard to push them right up and next to each other, even if they're relatively weak magnets. The closer that they get, the more they repel, the higher the energy that it takes for you to keep them there. It's the same way for our electron groups. They will repel each other. They will try to spread out as much as possible. Electron groups spread out as much as possible. And there are some shapes that we're going to learn. There's some names of shapes that we're going to learn. So we've got that to look forward to. You probably have learned all of these shapes depending on what chemistry you've taken before. Okay, our first shape, our first group. If you've got two electron groups, then you get a linear geometry. If you've got two things and they're around a central atom, the furthest that they can get away from each other is complete opposites, right? If my hands here are each an electron group, an atom, the furthest that I can get them away from each other is on complete opposite sides. And that'll have a bond angle of 180 degrees. A circle is 360 degrees, so 180 degrees. They're in a line, straight line, so it's 180 degrees between the two groups. And this is a linear geometry. I will also call, if we've just got two things bonded to each other, I would also call that linear. So I also call things like HCl linear. Some people disagree about that. It's just two things. The only thing that it can be, in my mind, is linear. I don't know what else other people would call it. But definitely if you've got two groups on the central atom, beryllium, in this case our central atom, then that's going to have a linear geometry. If we look at the Lewis structure for carbon dioxide, this also has two electron groups. We've got two double bonds. Also has two electron groups, and so it also has linear geometry. So anytime you've got two groups, only two groups, it's going to be linear geometry. We can also have three groups. And with three groups, that would be something like BF3, boron trifluoride. We've got trigonal planar geometry. The trigonal, the tri part meaning three. I think the gonal part here means points. It's been a while since I've looked it up, but it works at least. So 3 points, and then the planar part means flat. So it's got 3 parts and it's flat. Those are both important. There's a different type of trigonal that's not planar that we'll talk about later. So this is sort of like if somebody's doing the Y in YMCA when you're doing the dance. That's sort of the shape that we're looking at. And these 3 groups are as spread out as they can possibly be around this circle. It's because it's flat. And so it's 360 divided by 3, or about 120 degrees between each of our groups. This is assuming that they are all the same group. We'll talk about modifications to our bond angles later. But our bond angle for a trigonal planar geometry, where it's flat in the plane of the board, this is as separated as they can be, and they're going to have 120 degree separation. Question?
So we're just talking about electron domain geometry right now, not molecular geometry. Yeah.
We're talking about both right now.
Okay.
They're the same.
I thought
You can have lone pairs on the central atom, and then that changes. Your electron geometry and your molecular geometry would be different in those cases. We don't have lone pairs, and so they're the same. If we substituted in instead of one of these fluorines, if there was a lone pair, it would still be trigonal planar geometry for the electron geometry.
Right.
The molecular geometry would be a different shape because the electron group, the lone pair, wouldn't take up space. We'll get to that. So trigonal planar geometry, we can also have stuff like formaldehyde. Formaldehyde also has 3 groups. It's got 2 single bonds and 1 double bond. So it still has trigonal planar geometry, but it has slightly different bond angles. So our double bond has extra repulsive force than a single bond. So our double bond exerts more repulsion. How many electrons are in a double bond? The same thing you yell on the golf course, 4. At least if you're not very good. So 4 electrons in a double bond versus just 2 in a single bond. 4 is bigger than 2. They're all negatively charged, so it's going to exert more repulsive force because we've got more electron in there. And so we end up with slightly larger bonds, slightly larger spacing, larger angles, because of the increased repulsive force between the double bond and the single bond. The double bond is exerting more force, pushing the single bonds closer together, and so this side between the single bonds gets pinched down a little bit because they're pushed away from the double bond. If we had a triple bond here, it would be pinched even more, and so it would be even smaller of a bond angle than 116, if that was possible. You don't need to know the specific, like exact, it's 121.9 degrees, it's 116.2 degrees. That would be crazy. You should be able to make predictions about this bond angle being greater than 120 degrees, this bond being less than 120 degrees. So you should know the base, like for the form, for a trigonal planar, it's 120 degrees. And then how the double bonds, triple bonds, lone pairs, things like that will influence bond angles, ideally. Okay, a central atom in a 3-atom molecule forms 2 double bonds and has no lone pairs. What is the geometry of the molecule? Think about, write about, talk about what would that molecule look like? All right, we've got 3 atoms. Let's just call them A, B, and C. The central atom here is B, because it's between the other 2. A, B, and C are our 3 atoms. The central atom, B, forms 2 double bonds. And it has no lone pairs. So how many electron groups does our central atom have? It has 2 electron groups. It doesn't have any lone pairs. And so the furthest that these 2 things can get away from each other, A and C, the furthest they can get away from each other is linear. And so that's what they will do. This will be a linear geometry. What will our bond angle be? Yeah, it's going to be 180 degrees for our bond angle. All right, we can also have 4 electron groups. 4 electron groups gives us tetrahedral geometry. Molecules with 4 or more groups, which we'll talk about somewhat frequently, enter the 3-dimensional space, and they're a little bit harder to visualize. So if we use these balloons as an example, we've got pictures of balloons. Our balloons represent electron groups, and our central atom would be here where the balloons meet in the center. So for a linear pair, they're on opposite sides. Trigonal, this is sort of the trigonal planar. This is the YMCA shape. And then if we get to 4 electron groups, this is the most groups that I can represent with my body. This is like if you make an X shape and then you twist at the waist. So rather than being square planar, we can actually get these groups a little bit further away from each other by twisting, because it makes a little bit of space with this rotation part. So they get a little bit further away by taking up that rotation And what this looks like with balloons, right, is we've basically got 3 groups that are down and in corners of a triangle, and then we've got one up at the top, and we call this tetrahedral geometry. This tetrahedral means 4 faces. Tetra is 4, and the hedral part means faces or sides. And so this is the same shape as a 4-sided die, the singular of dice. And we would represent that sort of like a triangle-based pyramid. If you are not taking the makeup exam on Thursday, you're welcome to play around with the molecular modeling kits that we have for the molecular models worksheet / lab that we were going to do otherwise. Some examples of tetrahedral geometry, things like methane, CH4, has 4 groups. They're all single bonds around the central atom. Tetrahedral geometry, if all the bonds are equal, has 109.5 degree bond angles. And this is like the one weird one. I think the rest are all much more normal. 109.5 is a little bit of a weird number. But that's as separated as they can be. The Lewis structure that we draw looks flat, and these would have 90 degree bond angles. But again, that's like if you make a big X with your body versus if you turn to make the tetrahedral shape. That gets you a little bit more space, makes that maximum separation. So 109.5 is a number that you just get to memorize for fun. Well, for class, not for fun. Questions about tetrahedrons? Okay. What is the geometry of the HCN molecule given that the Lewis structure is as seen below? Which shape is this? Yeah, it's also linear. We've got 2 groups around the central atom, so it takes a linear shape. And what's our bond angle? We've seen it with single bonds only, we've seen it with double bonds only. Now we've got a single bond and a triple bond. It's still 180. So it doesn't matter what bonds we have. If you've only got 2 groups and it's linear, the furthest they can get away from each other is 180 degrees. Doesn't matter how strong or weak those groups are. It's always going to be that 180. And before we wrap up, I want to get into at least one of our newer geometries. So we've seen 4 electron groups. We're going to 5 electron groups. For 5 electron groups, we have trigonal bipyramidal geometry. So the bipyramidal part, bi meaning 2, pyramids being those things that lots of ancient civilizations made, not just the Egyptians. Right, the triangle-looking things with some sort of a base. So bipyramidal meaning that we've got 2 pyramids. We've got one pyramid that we usually view as going up and another pyramid that we view as going down. 3 of the groups lie in the flat plane, the way that we've drawn it at least. And we would call these equatorial positions. The equator, I think I'm spelling that correctly, right, on Earth goes around the widest part. It's like the middle. So equatorial positions are all pointing out towards spots that would be on the equator. or out to the sides. The other groups, the other two groups, are above and below the plane, pointing up and pointing down. They are along an axis. This would be the Z axis. Or up and down, and so we call those axial positions. Our axial positions are pointing up and down. Our equatorial positions are pointing out to the sides. And we have different types of angles here. So we've got two different types of angles. Between our axial chlorine and our equatorial chlorines, we've got 90 degrees. Since one's pointing up, one's pointing directly to the side. That's going to make a right angle, so we've got a 90 degrees angle there. Between our equatorial positions, right, basically on the equator, the flat part, we've got this Y shape again. So we've got 120 degrees between each of those, but then it would be like if I was impaled with a giant, like, pole or something, right, and there's a pole sticking out in front and behind. That's the shape that we're looking at here. So our axial positions stick up, equatorials stick out to the side. We have modeling kits that we can make these shapes with as well, to be able to see these in three-dimensional space, since it's a little hard to visualize them otherwise. Questions about our trigonal bipyramidal. It's trigonal because we've got three groups out on the equator, 3 points on the equator. Bipyramidal because we've got up and down pyramids. Okay, and then the last shape that we'll cover today is the octahedral geometry. The octa part being 8, like in octopus, and hedral again being sides or faces, flat parts. So our octahedral geometry, we've got 4 equatorial groups and 2 axial groups. So we've got a group up and down. We've got 4 groups out to the sides. And that looks like this. And all of the bonds are 90 degrees. Since we've got 4 that are out in the equatorial positions, the spacing between those is going to be 90 degrees, and between our axial groups and our equatorial groups, those are also 90 degrees. This is the biggest geometry we will talk about in this class. And so for something like SF6, we've got an expanded octet on our sulfur in the middle. That's how we're able to access such a large geometry. Questions? Okay, then that'll do it for lecture for today.